we go over rotation motion. So when you're talking about rotation motion, we're only talking about something that is moving in a circle. Well, now some things we need to get to understand when you're talking about rotation motion. So this rotation motion is divided into pure rotation motion So when we are talking about pure rotation motion, we treat the rotation of an extended object about a fixed point. So we are only talking about how an object is rotating about a fixed point. Let's say we have got a wheel. This is the fixed point of that wheel. So how is this wheel rotating about this point? So that is just pure rotation motion. Well, apart from pure rotation motion, what we need to get to understand here is another thing, rotation kinetics. So rotation kinematics, alright, kinematics. Now when you're talking about rotation kinematics, we are now interested in understanding the motion of something that is moving. So pure rotation motion, we are considering how something is moving, and rotational kinetics, now we understand how fast is it moving, how slow is it moving, but we are not interested in understanding the forces which are causing it to move. And then after that, now that's when we go to rotation dynamics. So rotation dynamics, now we consider now the forces which are causing something to start rotating. That is on rotation dynamics. Now let's get to understand how we work with rotation motion. Well, the first thing that we want to understand when it comes to rotation kinetics, that is the movement of something, rotation kinetics or kinematics. So firstly, we need to understand something called angular position. So the angular position is given in terms of the angle. So now this angle is taken the fixed point as the x-axis. So I want to give, for example, if you are talking about a circle, if we take this as a center, we fix this one, so this is the x-axis, we fix it. So if something is at this point, let's call it point A. So what is its position? We are going to give the angle theta from the fixed point x. Okay, so we take the fixed point as the x-axis. So the angular position is simply given in terms of theta. So angular position is equal to theta. Now, apart from understanding the angular position, we want to know the angular displacement. So now when it comes to angular displacement, you want to understand where something moved and where something now is in a circle. So let's say this object was first at this point A, where the angle from the fixed point, let's say the fixed point, the x-axis in this case. Okay, let's fix this as the x-axis. So let's say it was first at theta 1. That was its angular position. That was its position first. And then it rotated and then it came to this point. So let's say the angle is a theta 2 from the fixed point here. So the angular displacement is simply the change in theta. Theta initial and then theta final. So you consider the final position minus the initial position. That is how we get now the displacement. Just like in a straight line, if an object was at point A and then now it is at point B. So what is this displacement? It is this minus this. Okay, so that is how we consider it. So that is angular displacement. Well, apart from angular displacement, another thing that we want to get to understand is angular velocity. How fast is something moving around a circle? That is angular velocity. Now, angular velocity is represented by the letter omega. We know that if we are talking about just linear velocity, velocity is given as change in displacement over change in time. So same with angular velocity. Okay, angular velocity is going to be given as change in angular displacement divided by change in time. So that is how we get it. Well, apart from angular velocity, now we need to get to understand, because this is an angle, angles are measured in degrees or radians, but in here on this topic we are not going to be working in degrees, and so the SI unit for angular position is radians. So we give it in radians, maybe pi radians, 1.5 radians and such. So because of this, to find the unit for angular velocity, it is in radians, because change in theta is in radians, and then down it is in seconds. So therefore the unit is in radians per second. That's the angular velocity. Another thing that we want to get to understand is angular acceleration. So angular acceleration, the symbol is alpha. So we know that acceleration is the change in velocity over change in time. So if we're talking about angular acceleration in this case, the angular acceleration abbreviated by alpha is given as change in angular velocity, that is omega, divided by change in time. We know that angular velocity is in radians per second, and then divided by time, which is in seconds. So therefore the unit becomes radians per second squared. So that is it. So these are what we are interested in. So this is when we're talking about rotation motion, where all we are saying here is when something is rotating in a circle. Let me just show that. So say this is a circle. Now you are saying how fast is something moving along this circle. Say maybe a person is standing, and then there is a rope, and then they've tied a stone, and then they are rotating this rope. So this will be rotating in a circle like that, as this person is rotating it. So now how fast is it moving around the circle? How fast is it? That is what we mean by angular velocity, angular speed. So if this is the initial position, theta 1, this is the final position, theta 2. So from here up to that position there, how fast something is moving, that is what we are calling omega. How fast something is moving. But the acceleration from theta 1 to theta 2 is what we are calling as alpha. Now, using this same knowledge which we've mentioned here, let's go on and try to relate things in a circle and even things in a straight line. Now, before we do that, as we can see this circle, so just like I drew earlier, if you have got a person like this, and then is rotating this thing around, so there is always a force that is pulling this ball towards the center of the circle, such that it doesn't break off. So that force which pulls things towards the center is the centripetal force. Okay, so we have got a force towards the center, that is the centripetal force. So there is also an acceleration. How fast is something moving towards the center? That is called centripetal acceleration, or also referred to as a radial acceleration. Okay, so we have got radial acceleration there. So where we are saying AR is radial acceleration, also called centripetal because it is towards the center. Centripetal acceleration. Okay. Well, another thing that we need to realize is this. Just this person I've drawn here rotating a ball, immediately this rope breaks. When the rope breaks, this rope which is here, this ball will be pushed straight, and it will be pushed such that it will make 90 degrees with the force that is pulling it towards the center. So if it breaks, if the rope breaks and this thing moves at that angle, it is going to move at an acceleration called tangential acceleration. Why do we call it tangential acceleration? Because it always makes a tangent to the circle. So there is always, after a braking, this always moves in such a way that it makes a tangent to the circle. A tangent is a line that touches the circle at only one point. Alright. So we are saying we also have tangential acceleration there. Okay. Now, how do we find this acceleration? How do we just get to find it? So the radial acceleration or the centripetal acceleration is given as velocity squared divided by the radius. That is how we find the radial acceleration. So you are just going to divide the velocity at which this thing is moving, you square it and then divide by the radius. That gives you the radial acceleration. Well, now this velocity which we are using here is a linear velocity. We are going to understand that in a moment. Another thing to get to understand is that during circular motion with constant speed, so if something is moving around a circle with constant speed, we know that constant speed, just the word constant speed means acceleration is equal to 0. But how come when something is moving in a circle, acceleration changes? So acceleration changes not only because of change in speed, acceleration also changes due to change in position. So the reason as to why we have got acceleration during circular motion whilst there is constant speed is because position is always changing. We are always going in that manner. So position is always changing. It's different from a straight line. And so even if there is constant speed in a straight line, the acceleration is not equal to 0. This object is always accelerating every time. That is because position is always changing. Okay. So now, as we can see here, we have got tangential acceleration and radial acceleration, which is also called centripetal acceleration. Now, let me draw this as a vector. Alright. So we have got tangential acceleration going like that. We have got centripetal acceleration going like that. So if we draw lines which are parallel to the radial acceleration or the centripetal acceleration, and then the line which is parallel to the tangential acceleration, and then I join this, so this is going to give me the resultant vector in that direction, because this is going up, this is going this direction, so the resultant will be in that direction. So this resultant we are going to call it resultant acceleration. And so how do we find this resultant acceleration? Okay, so considering the direction, this is going, let me put direction like that, even this let me put direction like that, even this let me put direction in that manner. So this acceleration in that direction, which we call as the net acceleration or the total acceleration, is going to be equal to the sum of these two accelerations. So that will be et plus, at and ar. Now because we can see a triangle here and this forms a right angle triangle, so we are forming a right angle triangle at both this point and this point. So what we are saying is, if we get only this triangle which is down here, if this is AT, even this one is going to be AT. Because it is pointed up, even this is going to be pointed up. So I can remove this portion which is on top. Okay, in that direction. So we see that this total or the sum of the accelerations is actually can be gotten using the Pythagoras theorem. We can see a right angle here, and you know that the hypotenuse is equal to the two sides squared, and then we square root from the Pythagoras theorem. So the magnitude of the total acceleration is actually given by the tangential acceleration squared plus the radial acceleration squared, and then square root that. Okay, that is how we get that. Now that is what we also needed to understand here. Now another thing to get to understand when you are talking about circular motion, we have got linear quantities and also angular quantities. So angular quantities, we mean those which are in an angle, like those around a circle, moving in a circle. And then linear, those which are moving in a straight line. So we have talked about angular acceleration, angular velocity, angular position. We also have linear acceleration. We also have linear speed. We also have linear position. Alright. So now let's say this is the center of this circle. Then we can do that. And then let's say this object is moving, it comes to this position here. So the distance, if this is theta 1, this is theta 2. So we are saying the displacement here, angular displacement, as you already said, angular displacement, which is given as delta theta, is given by theta 2 minus theta 1. So that is the displacement, that is the distance from this point to this point. But we also know that if we have got a circle and then we cut with any 2 points like that, the distance from one point here to the other point, that is called the arc or arc length. So we can just say delta theta, the angular displacement, we can call it as the arc. So we're going to call the symbol for arc is S. That is also the symbol for displacement, we know. Alright, so I've got S. And we know that when you are talking about velocity, linear velocity, we said linear velocity is given as change in distance, and we know that distance is given by S divided by change in time. Alright, so that is it. So this same formula which is here, we can alter it. How do we find S? How do we find the arc? We know that S is the arc length. So if we are talking about a circle, the distance around the circle, that is called circumference of a circle, is given by 2 pi r. Now in this case we're talking about the arc length. So arc is just a part of a circle where the angle here is theta. So because we're only talking about a part of a circle, then it becomes the theta over 360. Now we are working in radians, so it will be theta over 2 pi and then times 2 pi r. Right, times 2 pi r. So that is where also the formula for circumference of a circle comes from. We know that the circumference of a circle, the angle here is 360 or 2 pi. So it is going to be 2 pi over 2 pi times 2 pi r. Then we just have 2 pi r. That is why we don't even put it there. Okay. Now we can see that we have got 2 pi and we have got 2 pi. Therefore, the arc length is just given by theta times radius. And so where there is change in arc, we are going to put, well, because it is change in arc length, here it is just arc length. If we put change on both sides, we are going to introduce change. Then this will also be change in position and then times r. Because I'm talking of change in arc, then it should also be change in the angle. Because just arc itself is just r times the theta. Now instead of me writing the r behind, let me write the r in front here. It's the same thing. And so in this formula where I'm saying change in s, I'm going to put that one. So velocity becomes r delta theta and then divided by delta t. Okay. Now this is what we have. Well, I can also say this is the same as v is equal to r. I put delta theta alone over delta t. But we know that delta theta divided by delta t gives us, we know angular velocity is given as change in displacement, angular displacement divided by change in time. So where there is this quantity, change in angular displacement divided by change in time, we are going to put angular velocity. So therefore, velocity, which is linear, is equal to radius times angular velocity. So this becomes the relation between angular velocity and also linear velocity. So the linear velocity is actually just equal to the angular velocity times the radius. That means the angular velocity is simply equal to linear velocity divided by the radius. In other words, we can make a general conclusion. Well, before I can even make a conclusion here, let's determine one more thing. So we said that radial acceleration or centripetal acceleration, the acceleration towards the center of a circle, is given by velocity squared divided by the radius. Now we have just seen that the velocity is actually can be given by the radius times angular velocity. This is the linear velocity. Linear velocity is equal to angular velocity times the radius. So where there is v, I can put r and omega squared divided by r. So this will give us r squared omega squared divided by r. So this gives us radial acceleration can also be found as r into r squared, that will just be r, then omega squared. So this is another formula that we get to use when we are talking about angular motion. Now a general description that we can give. We have seen that velocity is r times omega. Now we also know that acceleration, that is in a straight line, linear acceleration. Well, if this ball is moving, we said, imagine there's a person who is holding a rope here and rotating a ball. If this slips off, if the direction is like this, if this ball slips off, it will go like that, it will make a tangent. This tangential acceleration is also referred to as the linear acceleration. So tangential acceleration is what we are referring to as linear acceleration. And we know that tangential acceleration or linear acceleration is just given as change in velocity divided by change in time. Okay. Now we know that velocity is given by this. So if we are talking of change in velocity, then that is actually equal to r times change in angular velocity. So where there is change in velocity, I'll substitute r change in angular velocity. So r change in angular velocity divided by change in time. So I'm saying linear acceleration is equal to, I can put r alone and say delta omega divided by delta t. Well, we know that angular speed divided by divided by time gives us angular acceleration. So angular acceleration is given by change in angular speed divided by change in time. And so acceleration in the linear form is equal to radius times angular acceleration. So what can we see from here? If we have got anything linear and then angular, just multiply the angular by the radius, then you are going to get linear. That means if you are talking about linear speed, that is s, it is actually r theta. We already saw this. S is the arc length, and you know that arc length is given by r times theta. And then if you are talking about linear velocity, it's actually equal to radius times the angular velocity. If you are talking about linear acceleration, it's radius times the angular acceleration. So that is what we get from here. Alright, thank you so much for watching this video. See you in the next video where we're going to go over some practice questions. Now, having understood this, even as we go to some practice questions in the next video, you should not forget the laws of motion. Well, just the equation of motion, let me say. We know that final velocity is given by initial velocity plus acceleration times time. And another thing that we know is that final velocity squared is equal to initial velocity squared plus 2 times acceleration times distance. And also we know that distance is equal to initial velocity times time plus half at squared. Okay. Another thing that we know from here is that when you are talking about v plus u divided by 2, this is called the average speed. And you know that speed is equal to distance over time. So distance is given by speed times time. Now I'm using s to mean speed, but s doesn't mean speed in physics. S means displacement. So if we're talking about average speed, we say final speed plus initial speed divided by 2. So we are saying displacement can also be found by v plus u divided by 2 and then multiplied by time. So these are the linear quantities or linear equations. So if we go to angular, the same equations apply. So we know that v is omega, so this will be omega final being equal to u is initial speed, that will be omega initial plus acceleration becomes angular acceleration times time. So same here, we have got final speed squared now in angular form is equal to initial speed squared plus 2 acceleration becomes angular acceleration. Distance s in angular terms is the displacement, angular displacement represented by theta. And then this equation becomes s, which is the distance in angular terms is theta, and that will be equal to initial speed, which is omega initial times time plus half. Acceleration becomes just a, and then t squared, and then s is still theta, and that will be equal to omega initial plus omega final divided by 2 times time. So these are the equations that we use. Well, if you like the video, be sure to subscribe in order to follow more videos on the YouTube channel. See you in the next video where we go over practice questions.